So thanks a lot. Thanks to the Candela Foundation and also to the organizer and to Michael, of course, for this nice invitation. I'm really excited to be here. And I think it's a super nice idea to have this series of virtual talk and have the possibility to discuss the latest results. As you might have already guessed from the title of my talk, indeed, so I will try to focus a little bit, put, let's say, the different building blocks for the emergence of supersolidity in ultra-cold atom. But before doing this, let me actually take this opportunity to explain something very important. And so to show actually an important ingredient, which are really the atom. So in ultra-cold gas experiment, we are, let's say, more used to think about most probably, let's say, how to trap the atom, how to cool the atom, which incredible phenomena we can observe with this many-body quantum system. But we don't discuss, or the community was not used to discuss the atomic species of choice. So it was really not a very relevant, in a way, detail, although it's extremely important. And so then the first part of my lecture, I decided to, let's say, really collect some of the important properties of the atomic species I'm working with, because it's a rather special one. So I think it's really worth to dig into it also because you don't find it in textbook yet. And indeed, I mean, if we now look at the periodic table, so typically when you speak about laser cooling, so how to go to the quantum regime with, let's say, an atomic gas, mainly the discussion is centered on alkali atoms. So these atoms which are in the first column of the periodic table, which are very nice and very simple because they have only a single valence electron. So having a single valence electron, the energy spectrum of alkali, it's simple. And of course, all alkali share many different properties. But actually then over the year, the field developed enormously. So I want also to mention that in June, in the mid of June, we will celebrate the first time that the scientists during a conference presented the first figure of a Bose-Einstein condensate. And this was at the conference in Capri, and Eric Cornell was showing, let's say, really early data about Bose-Einstein condensation. So 30 years later, the situation has changed quite a lot. And now you can see now on how things have developed and how the periodic table is getting more and more color over the year. And so you can see that, okay, first there is a lot of white space still in the periodic table for the new generation to come, but also you can see that there are some color code. So I'm dividing atom in terms of color code. So this one has the alkali, typically Bose-Einstein condensate. In each of these, you can tune the contact interaction by the use of a technique which is called Feshbach tuning. So the blue one, including ytterbium, which is here, are effectively two electron atoms. So where they have really the particular things, being a two valence electron, so in the ground state you have a spin up and spin down, so the quantum number, the spin quantum number is 0, and also the orbital momentum L is 0. So they really realized a very nice setting for what is called the SUN physics in this system. And then there is, let's say, this family of red atom, which what they have in common is that beside the contact interaction, they have also some important magnetic moments. So they are little atomic magnets. Some are stronger, some are weaker, and that's the speciality. So all put together, so you have single electron, two electron atom, and the red one here, they're really multi-electron atom with this very strong magnetic moment. Now, digging a little bit more into detail, because I mean, it's not only how many atoms an atomic species have, how many valence atoms, but also how do they are organized, in which electronic shell. So here we really go back to basic atomic physics. And so you see that the alkali in the ground state have only one electron in a spherical symmetric electron orbit. And the alkali earth have 2 electrons in the S shell. Again, spherical symmetry in really in the charge distribution around the nuclei. But when you move to this very special family at the bottom of the periodic table, which is the family of lanthanide, sometimes also called rare earth atom. So now you might have heard all this discussion between Trump and Ukraine and the rare earth atom. So these are the lanthanides, which have this property to be strongly magnetic. They are highly used in several technological applications. So they are kind of a very instrumental, important atom. So now these rare earth atoms have the peculiarity to be what we call submerged shell atom. What does it mean? It means that the valence electron are occupying 2 different shells. One is the outer shell, which is S, so it's spherical symmetric. And if you can see here, these 2, it's fully occupied. So the outer shell is fully occupied, but the inner shell, which is highly anisotropic because I have an orbital momentum with very large orbital quantum number, so it's not fully occupied. So how many vacancies this F shell has, if it's 1 vacancy, if it's 2 vacancy, 3 vacancy, will determine how strong is the magnetic moment in lanthanide. So there is, let's say, really kind of a symmetry that you can see up to some point, up to more than half filled the F shell. So because of this, so you can already imagine that now we are putting the focus on these 2 properties, many electron and also anisotropic orbital distribution of the electronic charge. And this gives rise to really a plethora of atomic physics phenomena. So first, the many electron means that the atomic spectrum of lanthanide includes many, many atomic levels. The fact that there is an anisotropy in the electronic shell, this F shell anisotropy, means also means that the quantum number, the orbital quantum number are large, and this gives you 2 different phenomena. One, that you have a large magnetic moment, as I already mentioned, but the other one is that you have an anisotropy in the orbital distribution, which means also the electrostatic interaction, if you want, is anisotropic. So the van der Waals type of interaction. And of course, I mean, there is let's say, I would say, all a pyramid of consequence, let's say, really an avalanche of consequence coming from this. So the short range interaction is anisotropic, the long range interaction is anisotropic, the way the atoms are interacting with light is tensorial because it's dependent on angle, there is also an asymmetry, and you can enter finally to the physics of dipolar quantum dots with strong dipole-dipole interaction. Because of all these properties together, this lanthanide seems today to be a very powerful resources for ultra-cold quantum technology. And indeed, I mean, was identified as one of the main future direction for the ultra-cold quantum technology to come. I would like now to, let's say, dig a little bit more and really show you some of the things, some of the property I'm kind of summarizing here. So first, let's have a look at alkali. So alkali atoms, which have been the one originally Bose-condensed, laser-cooled, are very nice because they realize effectively a 2-level system in which you have a very strong cycling transition from the ground to the excited state, and they have also the nice thing to be all in the infrared regime. Now, if from alkali and a simple 2-level picture, you go to lanthanide, let's say that's the picture that you will have. You have really accessible to you, so in the sense that you can buy laser with proper wavelengths are commercially available. You can access a variety of different levels. And so I will go to this a little bit more in detail, but you see you have transition that span from the UV, so very short wavelengths, very high energy, to really to the far infrared. So let's have a look a little bit more in detail about all these levels. So that's the same energy spectrum. And as an example, I'm showing you the one of erbium. So that's the ground state, and you see that's the electronic configuration of the ground state. The color red or black tells you about the parity. So every light should couple state of opposite parity. So from red, we will go to a black line. And for example, this high energy light in the UV is extremely strong. So it's a much stronger transition than the typical laser cooling transition in alkali, about a factor of 10. And so this can be used for very fast cooling and ultra fast imaging. You have then now another interesting transition that is one called the intercombination line, because it's a spin non-conserving transition. So in principle should be forbidden, because normally spin should be conserved in the dipole transition rule, but in the intercombination line, that's not the case. Because erbium is heavy and all lanthanides are very heavy, actually the intercombination line are rather strong. Indeed, this one has about 200 kilohertz. Then you have another one, which is a weaker transition that goes to 8 kilohertz. And there, for example, you can think to study superradiant state by having atom really irradiated by this light, and also to have advanced cooling to reach even lower temperature. And then finally, very interesting, is a line which is kind of the ground state of the orthohelium, if you want, for this, especially in spectroscopy. And it's a very narrow line, it's 1 Earth. It's super interesting because it's directly from the ground state. It operates at in the telecom window of the wavelengths. And this is very, very interesting because you can use it as a clock transition. So you can do spin manipulation and any type of fine metrology on the transition at the level of 1 Earth. Altogether, I would say that by now, so we have several groups, of course, including ours, but not only, have used some of this transition really to reach many different types of results. Moreover, what is also very, very nice is that if you learn something about erbium, you can basically one-to-one transport to the other lanthanide. Indeed, look here. So that's the spectrum of erbium, the one that we went really in detail, and that's the spectrum of dysprosium. Dysprosium is more magnetic than erbium, but if you look at the atomic spectrum, it's basically very similar. You have a strong transition in the blue. Also here, you have the intercombination line, you have a clock type transition. So in this sense, they are all brother and sister. There is a very strong familiarity and sense of belonging in terms of the atomic properties. Now, let's say going even a little bit further in this, I would like to show, first of all, I mean, there is a review where you can see all the main results that have been achieved with lanthanide and with magnetic atom. And nowadays, using all these properties for laser cooling, manipulation, trapping, it was possible to create the first lanthanide Bose-Einstein condensate that was in the group of Benjamin Leb at Stanford. And he created a Bose-Einstein condensate of dysprosium, so where all the atoms are occupying the lower state. And shortly after, we did the same with erbium. But it was also possible, and unfortunately, I don't have the time to cover this chapter, which is extremely interesting, to demonstrate that identical fermions interacting by dipole-dipole interaction, they kind of will interact also in the ultra-low regime. So you can do direct evaporative cooling in identical fermions and really reach very low temperature and strongly degenerate quantum gas. It's also possible to take two of these atoms and to couple into Peshbach molecule that now will have a magnetic moment which is maximum twice the magnetic moment of the atom. So you are boosting even further the magnetic character of the atom. And then finally, as I told you before, really because all these atomic species are very similar, to create a quantum mixture Bose-Bose, Fermi-Bose, or Fermi-Fermi of two different lanthanides is really one of the most simple things. I worked in mixture of lanthanide in potassium rubidium and cesium rubidium, and I can tell you that the lanthanide mixture is really super easy because of this similarity in properties. And so, yeah, those are today all the atomic species from the lanthanide family, which have been Bose-condensed. The last one is Europium Bose-condensed in Japan. Besides this many body physics, very recently there is a new direction that have been developed, but also very interesting because also there the use of so many atomic transition is important, which is the possibility to really load a single lanthanide atom in an optical tweezer or in an array of optical tweezers. That's, let's say, our result, in which you can have an ultra-fast imaging or a non-destructive imaging, just using the properties of one optical transition instead of another one, and you can have an array of single erbium atom. And a similar result was also, let's say, reached with dysprosium in Palaiseau in France. Let's say, thinking about, let's say, very strongly focused light, and now these very anisotropic atomic species, this really open another, another chapter. That at least was for us. Now you put an erbium atom in a tightly focused optical tweezer, and you ask yourself, how deep is the trapping? What is the property? And then these all rely in understanding the atomic polarizability. Again, I mean, when you think about a two-level system like in alkali, it's very easy to think how the stark shift on the different atomic level is behaving, because it's almost a two-level atom. But when you and you can calculate how deep is your trapping potential using a formula which give you the potential depth, which at the end is typically harmonic if you use a laser beam, which is Gaussian, and then it's depending on the electric field on the laser beam you're applying, and then really special properties of the atom, which is the atomic polarizability. But now, if you have two-level atom, the atomic polarizability, which is basically the dipole matrix element that's in an atom-like interaction, it's easy to calculate. But if you end up with hundreds of lines and you have to account all these lines, the situation gets much more complex, because you have to, to get the polarizability, you have to account for the weight and the contribution of every possible virtual excitation from the ground state to the excited state. That's not the only thing. The other thing is that there is really also a very strong anisotropy. And so the fact that the atom have an anisotropy, what does it mean? It means that if you have a single erbium atom or dysprosium atom and you illuminate with the laser beam, it do make a change whether the laser beam is coming horizontally or vertically with respect to the quantization axis. And it do make a difference, the polarization of the light itself. So indeed, for this specific atom, the polarizability is not a number, so it's not a scalar, but has three contributions. It's a full tensor, which end up with three contributions, one which is a scalar contribution, a vectorial contribution, and what we call a tensorial contribution. This is extremely interesting. I mean, it sounds really complicated, but at the end, what is really nice is that you can have quadratic Stark effects, which are spin dependent. So by using these properties of having the coupling between the atom and the light being so complex, you can also shape type of trapping which are different for different spin state. Or you can, by changing simply the polarization of your light, make that every state feel exactly the same potential, which is the so-called magic condition. Or you can imagine a situation in which one type of spin state feel an attractive potential, let's say with the light is creating an attraction potential, and for the other spin state a repulsive. So it gives you a full playground just by changing polarization and direction of the light, without the need of changing the wavelengths, which is the very difficult things in our experiment, because the wavelengths will typical available laser don't tune the wavelength. So the wavelength is almost fixed beside some specific laser. And so here you can see, for example, how this is, let's say, a quantity which is proportional to the polarizability. And you can see that already in the ground state, the polarizability value changes sinusoidally, exactly how one would expect, changing the direction of the polarization. So one can go even further and go more in detail and see for which polarization, what's the strength of the coupling with the light. And at the end, I mean, if I really want to scare you, I want to show you maybe this figure in which all different energy level in erbium have a different polarizability and have a different behavior with the wavelengths of the trapping. So there is a little bit of digging that one has to do when you work with these atomic species, but what it's interesting is that you can realize any type of situation you would like to have. Okay, same trapping, very different trapping, one state untrapped, the other one trapped, and that's really very unique. Now, looking at, again, I mean, at the atomic spectrum, let's now focus on the ground state. And so the ground state, because the orbital number is very high, have a lot of MJ state. In particular, you can have more than 20 spin state in the ground state, so you can realize quantum physics with very large spin manifold. And then, of course, it opens also the question of once you have all the spin state, you want to have a deterministic, coherent manipulation of each of these spin state. And we have learned to use a clock transition, which is this one in the telecom window, only 1 Hertz line width, to really be able to tune completely and to produce any type of initialize the system in any type of spin population. There are several ways for doing this, and there are also this idea of using a clock transition to manipulate spin state have been pioneered in strontium in the group of Jun-Yi, but also a lot of experiment with terbium, and here I like to also cite the experiment at Lens by Leonardo Fallani. So our strategy is similar, but okay, a little bit different. What we do is we start with all the atom in the ground state, and then we apply a Rabi pulse to transfer all the atom in the excited state. And then what do? We do another Rabi pulse and another Rabi pulse, and we, let's say, go up to the ladder where we want. Indeed, here you see the example. We are putting up the atom in -5, and then we probe the -6. Those are the atom in the -6. So at the beginning, all atoms are here. You see it's 1, the population, and then it goes down because all the atoms are transferred here. And then in the second step, we can put all the atom back to the -5, and we can, follow this and repeat this in how many times and with how many steps we want to have. And here are, for example, an example in which we transfer all the atom in MJ = 0, so the non-magnetic state, or we create mixture of different types of systems. So the dipole, to add the spin degree of freedom is very interesting because the dipole-dipole interaction, so the long-range magnetic dipole-dipole interaction that I'm writing here, is, let's say now maybe this is a complex formula, don't care about this. This square is the magnetic moment square, basically. This interaction is long range because it's 1 over r to the cube, so it's so the atoms are seeing each other or even before colliding, and these are all the spin dependent of the dipole-dipole interaction, and it can be decomposed in basically 3 terms. So this equation can be decomposed in 3 terms, which I'm writing here, but let me give you simply the explanation of this 3 terms. The first one is an elastic term. Let's say it's just the collision between 2 atoms, elastic collision, which is the SZ term. Then you have this type of term, which is happening in this way after a collision, and then they kind of, so you have this atom and they split the spin. So it's kind of, this is a type of flip-flop type of collision, which is called the spin spin exchange collision, which is extremely interesting. Of course, I want to highlight already now that this type of collision is only possible if the energy that this atom is gaining to go up and the energy that the second atom is gaining to go down, it's the same, because energy should be conserved. So if in doing this, so sorry, I cannot do properly, in doing up and down, this flip-flop, so the energy should be conserved. If for some reason we would be able to take this excited state from one of the atom and push it up, this will stop immediately spin exchange collision. So it's a resonant process. So it means that energy should be the same. And then you have another term, which is inelastic, in which two dipoles are colliding and both of them are going down. This is called the dipolar relaxation. And we have also studied all these type of dynamics in which we prepare all the atom in the blue state. And so you see that part of the atom are going in the green state, that it's increasing, and part of the atom is going in the orange with this flip-flop term. And now, if we use our clock light again, and we kind of shift and put out of resonance this phenomena, you see that all the exchange terms are switched on. This is just one of the many examples one can give on how powerful it is to have a clock transition and this large spin manifold in the system. But of course, what is really very interesting, and this may be one of the most exciting parts, is really to go to the idea that we have two types of independent interaction in our system. One is the short-range contact interaction, and the other one is the long-range magnetic interaction. Those two interactions are completely independent, so can be tuned completely independent, and even the contact one, as you will see, have some surprise. So how to visualize, you have, let's say, a many-body quantum system of many atoms. You control the state of each atom, and these atoms are interacting to each other. What are the form of the interaction? So in the ultra-cold regime, the leading interaction, or the most used and known, is the so-called contact interaction, which I usually call it as a billiard ball interaction. So really, I mean, the atoms are kind of really colliding, and there is a scattering cross-section in S wave, and then the other type of interaction is, in the case of erbium and dysprosium, the very strong magnetic interaction. Now, what I would like one moment to put your attention is really about the contact one, because we are used to find in the ultra-cold gas experiment a very simple formula, which only depends on a parameter, A, which is the so-called scattering length. We know that already with alkali, and a very beautiful experiment by Wolfgang Ketterle, that this scattering length can be changed by the means of magnetic field using a phenomenon called flashback resonance. But and then you have the magnetic interaction. But what I mean, it's very special in lanthanide, is that even the contact interaction is anisotropic. So indeed, imagine to play billiard, but not having spherical ball, but imagine to have, let's say, ellipsoidal ball. The rule of the game is completely different. And indeed, I mean, it do make, so in this type of billiard ball, the energy or the scattering matrix for two anisotropic atoms colliding in this direction, so let's say like this, or head to tail, is completely different. So for the different possible orientation of the spin, there is one physics. So even the van der Waals potential has some anisotropy in the form of dependence on the quantization of the atom. And so you, I mean, a way to visualize this is to say, okay, I can expand the van der Waals potential in terms of multipole. So I would have the first term, which where the C6 is constant, like in alkali, but then I have another term, which is an angle dependence, and that's the first term. and then you will have the other term atomic, all the other orders. At the end of the day, all this means that we don't have only one C6, so the van der Waals curve is not one in the ground state, but you have many, many values of the C6, and as a consequence, many different energy potential one on top of the other. So lanthanides are a little bit in between molecule and alkali atom because they have many Bohr-Oppenheimer potential, and yes, and in the case, for example, of erbium, you have 40, I don't know, more than 40 Gerade and other 40, more than other 40 Angerade. As a consequence, the Feshbach spectrum, so let's say where you have this scattering resonance, is extremely dense in the case of alkali. And so what we have studied all the scattering properties. We put this Feshbach resonance in the context of random matrix theory, and we show indeed that there is the so-called chaotic scattering via the Dyson distribution of the resonance. I mean, here I don't have the time to go into detail, but if you're interested, here are some nice results, which by the way, it's not only for erbium, it's something general to lanthanide scattering theory have a hard time to be predicted for this very complex atom. So the scattering theory can more or less tell to the general density of resonance you will see, but it's very difficult to say, okay, if one resonance is S wave or D wave, and actually even the orbital quantum number of a collision is not really a good quantum number, so it's also not a very well posed question. What is the partial wave in the collision? You will have a leading partial wave in the same collision, but maybe not only one. But in a way, let's say it's not super important to assign all this resonance, because the important thing is that we can measure in different type of way the mapping between the scattering length and the magnetic field very, very, very precisely. And so here, this is really one example. We are even more precise than 1 A naught, and this will be very important for the next part. Okay, so here now, it's kind of, for me, the end of the overview of the properties of erbium. And maybe for me, it's now a good time to have a little break before starting the next part. Yeah, now, I mean, my aim was to show you the main properties, and by now you should know very well that actually we have a gas of ultra-cold atom, many of these atoms, and you should by now also know very well that there are two sources of independent interaction. One is the contact interaction, governed by the scattering length, that can be tuned using all this resonance, as I show you in the plot before. And so this interaction can be repulsive or attractive, depending on the sign of the scattering length. And you should know by now that we have the dipolar interaction. Something to really keep in mind of this dipolar interaction is that it's effective at long distance because of the 1 r to the cube, but also is depending on the orientation of the dipole. So dipole which are side by side, like in this orientation, they will repel themselves, like the magnet, like if you take classical magnets in your hand and you change the orientation, they will either repulse or attract. In this orientation, they are repulsing each other, while head to tail, so head to tail, they are attracting each other. Of course, if you now have 10 to the 5 atom in an harmonic potential, in a three-dimensional potential, atom can move. So there will be some atom that find themselves side by side and repel, some atom that find themselves head to tail and attract, let's say, in average. So this idea that you can have attraction and repulsion in both the two sources of interaction is very interesting, because we know in general there is one general rule of thumb, if you want to say, is that if you have an interaction which is attractive, so you have all these gas with strong attractive interaction, they will tend to be closer and closer to each other. But at some point, when they become closer and closer, there is a very, very strong density, and eventually the system will collapse. So the fate in general of a many body system with, for example, contact interaction only attractive is the fate to die, to collapse quickly. This is very general, it's not related only on, let's say, ultra-cold quantum gases. Indeed, also, you find example in the astrophysical star. For example, here I'm showing you the, let's say, simulation of a rotating protostar. So where the density is becoming stronger and stronger and stronger, and at some point there is the collapse of the star. This type of dynamic has been also observed with alkali atom, where the contact interaction was put in attractive by the group of Eric Cornell, and this was called Bose-Nova collapse. And this is obvious because increase of attraction is reducing the energy of the system. So the attraction is always, if you want, in the Hamiltonian term with the minus sign. So the energy gets lower by increasing attraction. So they will tend to increase more and more the attraction, and so to increase the density. And that's why the system has this runaway point. Now, let's go on with our example, because we have these two sorts of interaction that we can also independently tune and make one stronger, one or the other one stronger. But I think that one of the most interesting realization is to put these two interactions, so let's say the strengths of the interaction, equal. And let's, in our mental experiment, saying that we, for the moment, fix that the contact interaction is repulsive, so the system is stable from the point of view of the contact interaction. And we have now the dipolar interaction, we make it mainly attractive. How do we do this? I told you in spherical trap, the atom has as likely to be side by side and head to tail. But now if my trap is not a sphere and I start to deform and have an ellipse, I can have more atoms aligned in the attractive direction. That's what I'm now simulating or thinking to do. So in this case, I have that the strength, so the coefficients in front are, let's say, equally strong, but one is repulsive, the other is attractive. The type of interaction in a many body system is non-linear. So there is this n squared. Because of this non-linearity, there is this reinforcing of the attraction in the system. Because the system knows that by increasing the density, they can decrease their energy, and since the interaction is non-linear, that's exactly what they will do. There will be a tendency to make effectively the dipolar interaction stronger than the contact one, despite we started with the same initial strength. And indeed, this was observed many years ago in 2008 with chromium in the group of Tillman-Fao. What they saw is that a chromium Bose-Einstein condensate in a very, very, very short time would do this type of collapse, which, as you see, has a very peculiar shape of lower class, so like a D-wave shape here, which is exactly the D-wave geometry of the, let's say, dipole-dipole interaction. And so everything, in a way, is under control, because our physical intuition is that, okay, if you have nonlinear interaction, one source of interaction is attractive, the system will organize itself to maximize the attraction, and the attraction will bring higher density and finally a collapse. Everything was, in a way, clear. And so the next step, with the advent of lanthanide atom, was really to repeat this runaway B-wave collapse observed with chromium, but with much more magnetic atom. So, the question was what we will see the same things if we now use an even stronger dipolar attraction. And the answer to this question was, for us, for sure, we have to see the same. Now the attraction is even stronger, the collapse will be even faster, the atom will fly away even faster, and the system will die and the BC will be destroyed. But this is really now where a big enigma came in our community. And the big enigma started with an experiment by Tilman Fau, in which actually he saw exactly in this situation that the system would not collapse, but more would create a clusterized in very small Bose-Einstein condensate. All of these would be very small drop or condensate drop, if you want, and would organize itself in a type of crystal type pattern. And we live in this situation for a very long time. So it was a kind of a rather stable, if you want, pattern. So it was a lot, and he called it, so he and this group called it this type of distribution a droplet crystal. This is not, so all the drops are not coherent one to each other, and this is a long-lived droplet crystal. In our lab, we did also something like this, but in a slightly different geometry. And what we were creating is this type of state. Let me tell you, that's a normal Bose-Einstein condensate. That's the density profile of the system. And then by increasing the dipolar, the attraction, what we saw, as expected, is that the density would squeeze and become higher. But what we didn't expect, that at some point, when a critical peak density was reached, the system would stop to, let's say, evolve and would enter in a steady state, long-lived. And this new steady state is what we call it a single macro droplet. And this was really for us, I would say, a big enigma, and we needed really a new key, a new element to understand this enigma. The situation became even more enigmatic because if we now go back to the theory, so this was observed in the experiment, so we were able to create a stable condensate with much higher density than usual condensate. And if we go back to all available theories, so from, let's say, especially with this Gross-Pitayevsky that can deal with a large number of particles, there was no prediction of any stable solution. For all the parameters we had in the experiment, if we feed the theory with this parameter, there will always be a prediction of collapse. And so this is the main energy within the mean field Gross-Pitayevsky equation when you have the kinetic energy, the trap, the contact interaction, and the long-range dipole-dipole interaction. So there is no way to explain neither the droplet crystal observed in Stuttgart, neither the macro droplet we observed and also the Stuttgart observed, by the way. And this was really an intense debate. Something was clearly missing. And if you now look at the system, another very important property, also highlighted by the Stuttgart experiment, is that the expansion. So if we have now this macro droplet and we switch off the trapping potential, that's a gas, and you expect that if you break the container, the gas would expand. But in the case of a macro droplet, this was not expanding, but was really dropping. Is a gas that is dropping, let's say, under the effect of gravity, without expanding. This was also a very, very big surprise for us. So now, to summarize, in a way, we are now considering a many-body dipolar quantum gas in which you have repulsive contact interaction and attractive contact interaction. We saw that the ground state of this system is a macro droplet, but we don't really know why. It's not collapsing. We then did another set of experiments in which instead of having, let's say, this geometry in which the atoms are, let's say, mainly head to tail, so mainly attraction. So we turned the magnetic field and we had, so this, let's say, this geometry is all three-dimensional, in which the atom would be mainly head side by side. So it's a situation that realized repulsive dipolar interaction and repulsive contact interaction. Now we ask ourselves, what is the ground state or the stationary phase of this system? Of course, now we have only repulsion. So the answer to this question for us was very easy. We should have, let's say, a stable Bose-Einstein condensate, maybe a little bit deformed by the dipole-dipole interaction, but a stable condensate. And indeed, we saw this very nice condensate. That's the density distribution, and this is the, let's say, the image that we record in absorption. But what was really very surprising to us again is that if I now take the repulsive contact interaction, but instead of having a value of the scattering length 54, I just decrease by few percent, and I go to 44 A naught, what I see is that the momentum distribution of the atom changed tremendously. So we saw the spontaneous appearance, and this was back in 2017, the spontaneous appearance of two side peaks. This peak here and this peak here. And this was also a big surprise. Now, if you have a leading peak and two sideband, this always remember a bit, let's say, the interferometry type of signal you have, in which you have sideband and the central band. And this typically occur when you have a short wavelength modulation, give you some peak at very large momentum, because the wavelength and the momentum associated are, let's say, Fourier conjugates. If one is small, the other is big. So this was then our first guess, that somehow the system would acquire a modulation spontaneously. But we had really to debug why. And so a spontaneous modulation, what let's say the kind of easy way to think about this for us at the time was that, okay, we have a ground state, which is a steady state, stationary, very calm, and that's our fluid. And something was exciting maybe our system in a way of shaking or giving a modulation, and then there would be, let's say, the state of the system would be a wavy one. Now, when we think about something is exciting in many-body quantum gas, it's equivalent to ask ourselves what is the spectrum of the collective excitation of the system. So the knowledge up to this point in the experiment was that the spectrum of excitation of a normal Bose-Einstein condensate at large momentum is quadratic, like free particles, so non-interacting particle, and then at low momentum would be linear, acquiring this phonon type of excitation. However, if you add the dipole-dipole interaction, in many years before our experiment, it was discovered by theorists Luis Santos, Jora Shlapnikov, and Maciek Levenstein, that the spectrum of excitation, where you have the collective mode, so that what are the frequency at which collectively the coherent state, the macroscopic coherent state would be excited, had a very different shape, which starts linear, so phononic, arrives to a maximum called maxon, and then has a quadratic minimum, which is called roton, in analogy with helium. And indeed, so the way we explained the appearance of the side peak was really the softening of this roton minimum, so that would touch zero and would create this modulation. To confirm our idea, we then later really calculated and measured the spectrum of excitation. Of course, when you calculate, you need to consider that you have a finite system, everything is discretized. So you see this blob that are coming, it's kind of the different mode of a trapped finite size system. And now by decreasing the scattering length and making more and more important the contact interaction, this is more or less the type of in a way, is the type of spectrum excitation that you would see with the appearance of this minimum, which is the roton minimum. And we did that then using a technique called Bragg spectroscopy. We wanted to measure the spectrum of excitation. And here you see the phononic part when the contact interaction is very high, and then the appearance of the roton minimum into the system. This type of spectrum here, which has a phonon and a roton, actually it's really reminiscent of the spectrum that was predicted many years before and also observed by Landau for superfluid helium. In the case of superfluid helium, so it's really helium liquid, which has below a certain temperature superfluid properties. And let's say in the 47, Landau was predicting that the spectrum of excitation that superfluid helium should have in order to explain the thermodynamic properties and its capacity in particular should have this type of quadratic minimum at large momentum that he called Roton. And then many years after, actually this was then measured in experiment by Glide and collaborated in 94, and they could really measure that indeed helium superfluid has this pronounced Roton minimum. How to visualize the two types of excitation, photon and Roton? I mean, the photon are an excitation with a very small momentum, so very large wavelengths, and so it means in space it's like a jelly oscillating with a so the size of the oscillation is the full system size, if you want. While in the case of the Roton regime is opposite, so it's a very short wavelength and large momentum. So it's basically the creation of wave into the system. Interestingly, Landau, that's a bit of historical note, used the word Roton because he was thinking, okay, this special collective mode, from where it's coming from. And so his hypothesis, that then was wrong, was that the Roton was kind of the shadow or the ghost, as he said, of vortices, quantized vortices. So he thought that these, special value here, where the spectrum goes down, it's related to vortex dynamic into the system. But actually later, Nozière, many years later, was giving a different interpretation, and this was the correct one, and was interpreting that the Roton is the tendency of this fluid to become crystal. So it's kind of a tendency to a crystallization instability. All this opened in the condensed matter physics a lot of different direction of research. Now, to put a little bit in context from a completely different community than ours, there were then the question of, okay, you have a superfluid, and then there is this tendency to crystallization. Can the superfluid order, which is really delocalized order with macroscopic phase coherence, be simultaneously present with a crystal? Can a crystal be superfluid? And so there were a huge debate on this topic. I mean, Nobel Prize winner Penrose and Onsager were against this idea that these two orders could survive simultaneously. But there were also another number of theorists back in the mid-late 50s, like Gross, Young, Andrei Lifshitz, and then later Leggett, that were indeed thinking that quantum mechanically a state which would have localization and superfluidity at the same time would be possible. And this state is the one that we now today and call it, following they coined, so in this early theory paper, you find this name of supersolid, which is in a way paradoxical because all the particles are indistinguishable. And so each particle, you cannot say which one is localized and which one is flowing as a superfluid. And so this creates a sort of entanglement between these two properties. And in our case, this is really directly related to the softening of the Roton in the case of ultracold atom, because it costs absolutely no energy to create these let's say, periodic modulation of the density, which is actually what you have in a crystal, a periodic modulation of the density. It costs no energy. Now, the question is only now it's remaining whether this is an excitation or is a new ground state. And here it's, let's say, really where we come to try to understand more about. So our early observation, so that was the one that I show you with the softening of the roton and the appearance of the sideband. We then, in this early experiment, we were following the population in the roton mode. And so you can see that the number of atoms starts to increase. So the roton population increases. So we are populating this minimum at high momentum. But then at some point, the population saturates. And this was extremely strange for us because this is not what we would expect if, let's say, a mode gets to zero and eventually would bring instability, maybe a roton collapse, a roton instability into the system. And so, in a way, if you have the picture of creating exponentially divergence of excitation, which costs no energy, then the excitation should increase and the system should collapse. While again, we were observing something very, let's say, stationary after a while. So they reach a certain amount of population, this sideband, and then they stay. And this was also very interesting for us because indeed, in this early paper, I like to put really the archive here because I think the referee didn't really completely understood what we were doing. And we really pointed out that this type of stabilization might be related to the entrance into the supersolid state. This picture was very soon after then highlighted or confirmed by theoretical investigation by Ropuzzo and then Cillotto. We're using, let's say, our result about the roton softening. They show that this actually is, let's say, a supersolid behavior into the system. So the system, instead of collapsing, will make a phase transition to a new ground state. And the key to really unlock and understand everything is to realize that in our equation that we're describing the system, the Bose-Einstein condensate, there was one term missing. And this is a term that stabilizes instability. So by the roton softening, the stability is stabilized by this additional term that now we know is due to the so-called quantum fluctuation. The particular aspect of this term is that it rises faster than the interaction term with density. So at the beginning, the prefactor is very low and the quantum stabilization do nothing, but when the density increases at some point, it is a regulator, it stabilizes the maximum density. And this term is able to explain both the macro droplet and the stabilization of the roton softening. And so when all these ingredients were put together, plus many more additional experiments, so we could simultaneously also with the group of Tillman, Fau, and Giovanni Modugno, really, let's say, getting a very clear picture of this phase transition from a Bose-Einstein condensate to a new ground state in which the gas spontaneously create periodic density modulation. And so this is what we call supersolid. It's not an excitation, it's really the stationary ground state of the system. It breaks the translational symmetry spontaneously because it spontaneously creates, let's say, this type of, let's say, periodic distribution in density. But at the same time, there is global phase coherence. We can measure the phase coherence by using, let's say, all the technique of interferometry, of matter wave interferometry, and we can directly see in our experiment, let's say this is the different interferometry in time of flight, and we can see the interest density distribution of the supersolid. From all our data, it's possible to extract the phase, so via the so-called phasor. I'm not entering the detail, and you see that there is a macroscopic phase coherence because the phase is not random, but it's more or less staying in one region, plus some experimental imperfection and a bit of divergence due to temperature. Now, every ingredient is there. We understood that there is a new phase of matter that dipolar quantum gas has. We could calculate the full phase diagram in terms of atom number and scattering length. And you see the gray region is a Bose-Einstein condensate, a normal one. But when we decrease a little bit the scattering length, we enter in the pink and in the blue region. In the blue region, we have this array, this droplet crystal that was observed back in 2015. So it took some years for us to put all the pieces together and understand in where every, let's say, density peak is disconnected from the other. So there is no global phase coherence. And then in between, there is the sandwich between the crystal of droplet and the BEC. There is this very special phase in which you have modulation, but there is full connection, the particle moving the whole system. This is a way, let's say, one of the original way in which supersolidity was, let's say, achieved, is to prepare first to cool down the system into a normal BEC, and then to change the scattering length and to enter in this phase transition. This, of course, give a little bit of excitation and so on. And so that was the idea. So we start with the thermal cloud, we lower the temperature, we create a Bose-Einstein condensate, we then do a change in the scattering length, and we have this modulation here. But actually, there is also another way, much more powerful, that we in Innsbruck have really mastering now, and it's to directly pull a thermal cloud into a supersolid. We can directly do this. This is a much less excited state. It's really the ground state. It's much more robust. You can have it a very long lived. For us, the supersolid in our experiment lasts seconds. And moreover, you can use this technique of directly cooling in a supersolid by using different geometry. And so I want to show you that it was possible using this to go to have a fractional quantum phase transition from a one-dimensional supersolid. So the atoms are 3D, but the periodic modulation is only in one dimension. So now if we increase the atom number and change the trap, you see here you have these two density peak, and then you can have more density peak. The structure starts to become more and more two-dimensional, and then even more two-dimensional, and then getting, for example, ending with this very beautiful two-dimensional circular supersolid. This is definitely a very interesting state because this state has cylindrical symmetry, and so it's very interesting, the rotational dynamic of cylindrical symmetry system. And indeed, this is a relevant question because one of the real smoking gun for superfluidity, so while the breaking of the translational symmetry is clear because we see that it's not uniform, but you have density peak, the phase, the superfluidity properties is less clear in the system. So you can get the phase coherence, but really the thermodynamic properties of superfluidity are difficult, are much more hidden. And the fingerprint is the creation of quantized vortices. And indeed, I mean, what distinguishes a normal liquid from a superfluid, it's really the response to rotation. If you have now a bucket full of liquid and you start to rotate, if this liquid is a crystal one, what do you see? You see a big whirlpool in the center. But actually, if it's a superfluid, you see nothing. The fluid is not rotating. It's not coupling. There is no friction between the fluid and the container. So there is no coupling between them. It's not rotating. Only if you start to increase very much the rotation frequency, the system starts to develop this after a critical velocity, starts to develop these quantized vortices. And so this is really the fingerprint which have been observed in helium superfluid, in Bose-Einstein condensate, in the degenerate Fermi gas, in the strongly, so in the BCS phase of the degenerate Fermi gas, in superconductor is the main fingerprint. So we wanted to see the same, and now we had this nice cylindrical symmetric two-dimensional supersolid. That was really the main request. And so that's now, I will show you what is the idea for us, how to rotate a supersolid. It took us 1 year, so it's not an easy experiment, I really have to say. And the idea is that if you have dipolar atoms, they are all aligned with the external magnetic field because they are magnetic atoms, so they're little atomic magnets. If I rotate now the magnetic field, the atom would rotate with it. And so basically, what one can do is the equivalent of what has been studied in ferrofluid. If we now rotate a magnetic field, the system will follow. And we tested this into a normal BC. So what we did is we prepared our system. So now it's not in the supersolid state, but is in the normal BC. We are rotating the normal BC and we start to rotate. And now what we see is exactly the simulation and the experiment that show really the dynamics and the creation of quantized vortex in the dipolar BC. And we wanted to do exactly the same with the supersolid. Now this is a supersolid with 4 droplets. So you see now it's just our numerical simulation by rotating the system. And this is the experiment. So we were able for a very, very long time, because vortex need a lot of time to nucleate, we were able to rotate our supersolid. For the observation of vortex itself, this was a little bit, let's say, difficult and easy at the same time. It's difficult because imagine to have a labyrinth like this one. Now, in the labyrinth, in between the wall of the labyrinth, the density is very low. And that's how it is in a supersolid. Between the density peak, so in between the density peak, the valley is very low. So it's very hard to distinguish a zero density from a low density between the wall of a supersolid. On the other hand, it's very easy to nucleate vortices because since the vortex don't have to to really remove matter and create a hole in the density, it can simply move towards the wall of the labyrinth. The vortex created can enter very easy the system. And this is now what we observed. And so now let me just give you the results. So which means that the critical rotation frequency needed to have vortex inside the system is much lower for a supersolid than for a Bose-Einstein condensate. But we still remain with the problem of observation. And what was the idea? The idea came from the group of Sandro Stringari. Indeed, here, look, if we now have a normal Bose-Einstein condensate and we rotate, the vortex is very clear, is a hole in the density. But if we do the same with the supersolid, you cannot say where the vortex is. The vortex is here, but you hardly distinguish the region with vortex and without vortex. So our idea was, okay, we can change the scattering length and melt the supersolid at the same time only for observation. And so if we melt then the supersolid only for observation, then we can see very clear the vortex. And this is what we have done. And indeed, we start either with a BC or with the supersolid state. We rotate the system very slowly, no vortex in the BC, no vortex in the supersolid. We rotate very fast, and we see a vortex. I mean, the contrast is not very nice, but we see the contrast in the supersolid, in the BC, and in the supersolid. But then in between, there is this region where for a supersolid it's easy to get a vortex, and for the BC, no. So this was one way for us for directly observing the vortex, while for directly observing the phase winding, what one would say is that if we now have a 3 coherent state that expand, just let's say matter wave interferometry, and there is no vortex, that's the type of expansion that you would expect. And if you now have a vortex, so a hole in the density and the 2 pi phase winding, you will see that at the center there is no matter. And this is also what we did in our experiment. That's the case where we were rotating very slowly, so no vortex. And you see there is this very epsilon here and epsilon here. And if we had the vortex, that's the field. Okay, I think with this, I'm almost ready to conclude. But before doing this, let me thank the fantastic team that did all these experiments. I mean, we have many more results than what I could show you now, so you can find all the detail in our website. And we have 4 teams. So one is the erbium team, the other is the erbium dysprosium team, then we have the tweezer team, and we have a theory subdivision. And of course, we have, as everybody else, very interesting opening for PhD postdoc, and also very interesting postdoc in the theory team, because Tom just left. And with this, yeah, we are also building a new experiment in San Sebastian, so there are even more opportunity there. So it's a very nice new research direction of the institute that we are leading. And with this, let me thank you.
Okay. Do you calculate frequency-dependent polarizabilities for lanthanides using quantum mechanical methods like ab initio or DFT?
So the calculation for the theory calculation for the atomic polarizability have been done in the group of Emecoton laboratories in France. So they're really experts, Olivier Dulieu and Maxence Lepers are really, Maxence in particular, the one collaborating tightly with us. And I think they use the so-called Cohen code plus spectroscopic data. Not only the one, so spectroscopic experimental data, not only the one that you can find in NISTA, but also additional data.
Thank you for the great lecture. I have 2 questions. What does the word spontaneously mean in the context of the transition to the supersolid state? And how does superfluidity manifest when supersolid encounters an obstacle?
So the first question, what does spontaneously mean? In general, I give you really a general answer. In terms of a phase transition, a spontaneous symmetry breaking is when the symmetry of the wave function, so the solution of the eigenvalue problem, is different than the symmetry of the Hamiltonian. In our Hamiltonian, there is no term that have the wavelength of the periodic modulation. So the Hamiltonian itself, there is no, it's not like I put an optical lattice which have these wavelengths and then I see the state with the same wavelength. That's not a spontaneous symmetry break. Spontaneous symmetry break is a new symmetry emerging in the wave function that is not present in the Hamiltonian. And that's the first question. Now, the second part of the question is how the superfluid manifests when supersolid encounter an obstacle. So in the way this question is phrased, let us thinking that the superfluid and the supersolid are 2 different things, while is exactly the same thing. The supersolid is a superfluid state, okay? Now, if we would drag an obstacle inside a supersolid, you will see probably the existence of the 0, first and second sound, so the different sound of the system, similar of what you would see to, I don't know, helium superfluid. Just you need to drag in a way to not destroy the state. And that's the difficult part, because now you have all this peak vector gas, and now if you go with, I don't know, resonant light, you can destroy the droplets, okay? Because it's not a uniform in space. So you would have to be able to put this excitation in your labyrinth and find the right way. This can be challenging.
Next question is this. Hi, thank you for your talk. Could you give an outlook for trapping erbium in tweezer arrays? Are you looking to simulate Hamiltonians using both magnetic and Rydberg-Rydberg interactions?
So both the magnetic and the Rydberg-Rydberg interaction are long-range interactions. So the Rydberg-Rydberg interaction has been studied, studied for doing things like also, I don't know, Heisenberg Hamiltonian, spin Hamiltonian, all these things that you can do simply with magnetic atom into an optical lattice. These 2 systems in a way can address similar physical questions in different ways. However, one has to keep in mind that the Rydberg interaction is much stronger than the magnetic interaction. So once in my atom in the tweezer are promoted into a Rydberg state, the magnetic moment play no role. So it's not a situation where I can study competition between two different long-range order interaction. Of course, then never say no in quantum physics, because now someone can come up with an idea of dressing, of having very mild Rydberg interaction that can compete. Okay, but let's say, generally speaking, if you don't use any dressing, the Rydberg interaction is much stronger. So our intention in the tweezer is indeed to study Rydberg excitation, but the reason is not to combine with the magnetic one, but the reason is to use the multi-electron property of Rydberg. Now, to give you just an idea, if you have alkali, you have one valence electron, you promote this valence electron to the excited state, the core, the ionic core, it's not trappable. Indeed, when we say Rydberg tweezer is a mistake. Every experiment, every talk that speaks about Rydberg tweezer is not rigorous, because you have ground state tweezer, ground state atom into the tweezer. As soon as they are excited, the Rydberg state don't see the tweezer anymore. The polarizability is almost zero. Okay, so there doesn't exist Rydberg atom trapped in the tweezer. That's really a misconception somehow. But if you now don't have only one valence electron, but you have 14 that are kind of there to guarantee the polarizability of the ionic core, you take one of these and you promote. The other 13 are staying nearby the core and guarantee a very large polarizability. And there you can really speak about Rydberg tweezer. That's our view, but there are no theory. All this is blue sky research. So nobody knows really, okay, we can do some easy equation, but life is more complex and we can miss or be completely out of order of magnitude. I don't know but that's the idea. It should be like this, I think.
Because theory is quite hard. So we were thinking about using the circular states in this, but if I can ask questions, so you presented transitions from 1D to 2D. What about 3D? Is it obtaining supersolidity in this kind of systems in 3D feasible, or does this?
No, I don't think that in 3D those are feasible, because what you would, so the droplets are elongated, are really like tube. They're elongated along the dipole, so you have. The maximum you could do is in 2D. You will not have an interaction that splits additionally.
Mm-hmm. Yes,
as usual, never say never in quantum physics, but let's say you would need to maybe add on top of this spin orbit coupling that break the transition from another direction. You will have to add something else, which is not clear what at the moment.
In the case of Bose-Bose mixtures, we have LHY fluids, where quantum pressure is stabilized entirely by quantum fluctuations. Are such fluids observed in dipolar BECs? Additionally, can we have supersolids that are entirely stabilized by quantum fluctuations?
Exactly. So ours, maybe I was not clear. The supersolids are stabilized by quantum fluctuation. Indeed, the existence of Li-1-Yang term was first observed in dipolar, was first predicted by Dima-Petrov for mixture, then observed in experiment with dipolar gas, and then extended to alkali mixture. Okay, but all these are stabilized by beyond mean field effect, by the so-called Li-1-Yang. The specific form of the Li-1-Yang, so the prefactor, is a little bit different if you have only interspecies interaction or you have dipolar interaction. But the idea is very much the same. Yeah, it's the same functional dependence on the density.
Okay.
So if I can use the opportunity to ask one more question from myself. So, because I was very much excited at when you produce Feshbach molecules of erbium. So, but do you plan to follow molecular paths and observing some molecules producing it in the ground state, or is somehow it's not my interest at the moment because there is too many other interesting things?
So let's say at the moment there are so many new experiments on erbium and dysprosium that I think for sure this will come on the spotlight in no time from now. in general, if there was an attitude in, let's say, alkali composite molecule to hunt for the most dipolar one. And as you know, better than me, the electronegativity difference between two different lanthanides is very small because so the electric dipole moment of ground state lanthanide-based molecule is not zero, but it's not very high from what we expect. This can be an added value because there you can really create competition between different order, one governed by the electric field and the other by the magnetic field. And I think this is very interesting. What we are now seeing, I mean, there is a lot of new research. At some point, I mean, we should maybe get a separate Zoom and discuss it with you. It will be very interesting because we see spin flashback resonance with very interesting behavior uncommon, and this is another chapter.
Okay.
Okay, since I think we have no more questions this time, let us all conclude today's lecture and thank Francesca once again for her outstanding lecture today, and also Michał for his input and as co-chairing of this lecture series.